I am Dr. Basir-Ahamed-Khan, Assistant Professor of Physics, Krishnath College. This is the first lecture of Module 12. In Module 12, I will discuss the chapter Low Temperature Physics. The topics of these modules are, in this chapter Low Temperature Physics, are Joule-Thomson effect or JT effect, Joule-Thomson porous plug experiment, Joule-Thomson effect versus reversible adiabatic expansion. Next, enthalpy change in Joule-Thomson expansion, then Joule-Thomson coefficient, then Joule-Thomson effect for ideal and real gas, and lastly the temperature of inversion. Now today in my first lecture of this module 12, I will discuss these three topics in my first lecture. This is low temperature, Joule-Thomson effect, or in abbrevious JT effect, Joule-Thomson porous plug experiment, and JT effect versus reversible adiabatic expansion. Today I will discuss these 3 points in my first lecture 1. Now first point is that, now what is Joule-Thomson effect? Now what is Joule-Thomson effect? Now when a highly compressed gas is forced to pass through very fine holes means how? Now suppose here I draw a piston here. Suppose this is a piston. Here is a porous plug, tightly fitted a porous plug. Porous plug is nothing but a woolen or cotton. Is a cotton or silk. Here is very fine holes are there. That's why this is called porous plug. This is called porous plug. This is called porous plug. Is made with woolen or cotton or silk. Porous plug. This is made with porous plug. Porous plug made with woolen or cotton or silk. Here is a piston. This is pressure P1. Suppose initial pressure is P1. This is final pressure after expansion. The pressure, this is P2, where P2 is very small than P1. Now I repeat again. Now what is Joule-Thomson effect? Now when a highly compressed gas is forced to pass through very fine holes or pores to move into a region of low pressure. Here P2 is a region of low pressure. Then the process is known as throttling. That means when a highly compressed gas is forced to pass through very fine holes or pores to move into a region of low pressure, the process is known as throttling. Now at the end of the throttling process, it is found that there is always some change in temperature of the gas, and it is obvious. Now if I compress a gas, the temperature of the gas will change. So at the end of the throttling process, it is found that there is always some change in temperature of the gas. This effect of temperature change due to throttling is called JT effect. So this effect of temperature change due to throttling is called JT effect. Now what is throttling? Now throttling is when a highly compressed gas is forced to pass through very fine holes or pores to move into a region of low pressure. That means we have to compress a gas, and passing and forced to pass through very fine holes and move into a region of low pressure. This process is called throttling, and after the end of the throttling process, the change due the temperature change of the gas will occur, and the effect of temperature change due to throttling is called Joule-Thomson effect or JT effect. And after passing through the pores, the gas expand, and hence the throttling process is also called Joule-Thomson expansion. This is porous plug. This is porous plug, and after expansion, the P2 is the pressure very low pressure than P1. P2 usually the pressure atmospheric pressure. P2 is the atmospheric pressure, and P1 is very high pressure, and hence after expansion the change of the temperature will change of the gas, the temperature change occurs, and this process is called JT effect or Joule-Thomson expansion. Now the next point, the Joule-Thomson porous plug experiment. Joule-Thomson porous plug experiment. This is the experimental arrangement. This is the experimental arrangement of Joule-Thomson porous plug experiment. Now P is the compressor. P is the compressor. I compress the gas with pressure P1. P1 is the initial pressure, and P2 is the pressure after expansion. P2 is the pressure after expansion, and B is the porous plug. Here B is fitted, tightly fitted with a tube A. Here B is the porous plug made with cotton wool or silk, and T1 is the initial pressure and T2 is the final pressure. That means after expansion the temperature of the gas is T2, and to fix the temperature, the initial temperature, in this experiment the gas is first passing through the constant temperature bath C. Constant temperature bath C. Here the temperature of the gas initially the temperature of the gas is fixed with the constant temperature bath with temperature T1. That means the initial temperature of the gas before compression, the temperature of the gas is T1, and after expansion the temperature of the gas is T2. Okay, now the process is that first a gas is compressed with temperature, the gas is compressed with pressure P1. Gas is compressed with pressure P1, and the gas, to fix the initial temperature with T1, passing the gas through constant temperature bath, and then compress the gas, and after passing through the very fine holes through the porous plug, the pressure of the gas is P2. Now P2 is generally the pressure of atmospheric pressure, atmospheric pressure, and P1 is more greater than P2. Now this is the experimental setup, and if the initial temperature T1 is sufficiently low, then after expansion in porous plug experiment the gas becomes cool. I repeat again, if the temperature of the initial temperature of the gas T1 is very low, initial temperature of the gas is T1 is low temperature, sufficiently low temperature, that means for a particular gas that initial temperature should be a temperature of its critical temperature, because after, if the initial temperature is greater the certain temperature, initial temperature of the gas is greater than the certain temperature, then after expansion the gas becomes hotter instead of cooled. But the initial temperature is sufficiently low than the certain temperature, then we get, after expansion the gas becomes cooled in porous plug experiment. Now suppose the gas is cooled after expansion, then the cooled gas is again, the cool gas is again put into the compressor and again compress the gas, and again we get, after expansion we get the temperature becomes lower than the previous temperature. Now again temperature cooled, then again I put the gas successively or cyclic way, put the gas here and again compress the gas, and after expansion or after passing through the cross plug the gas becomes more cooled, and this process is called regenerative cooling. Cyclic way we change the temperature of the gas after expansion, and this is called regenerative cooling. Regenerative cooling. Regenerative cooling. Regenerative cooling. I repeat again this point. Now what is regenerative cooling? Suppose the initial temperature T1 of a gas is very low, that means the temperature T1 is lower than a certain temperature for a particular gas. Then after expansion we get the gas becomes cooled. Now we put the cooled gas again into the chamber here and compress again the gas, cool gas, and now after expansion we get, the temperature of the gas becomes cooler, and again we put the gas in this chamber, and again after expansion, after compressing the gas, and we get, after expansion the temperature of the gas becomes more cooler, and this, in this cyclic way we get the temperature of the gas, repeatedly the temperature of the gas becomes more cool and cool, and this is called regenerative cooling. I want to say here, the point is that if the initial temperature T1, is not lower than the certain temperature of a particular gas, then after expansion the gas becomes hotter instead of cooled. If the initial temperature is not less than the certain temperature, and if the initial temperature is equal to the certain temperature of a particular gas, because for a particular gas the certain temperature is varying, if the certain temperature is equal, initial temperature is equal to the certain temperature, then after expansion there will be no change of temperature. So this is the output, or this is the result of Joule-Thomson porous plug experiment. Now the next point is Joule-Thomson expansion versus reversible adiabatic expansion. I want to say that here The reversible adiabatic expansion, when occurs the reversible adiabatic expansion, during the process the whole system is in equilibrium state. But I have already seen that JT expansion through the during the process or during the Joule-Thomson expansion, the system is in non-equilibrium state. That means reversible adiabatic expansion, in every passage or during the process, the system is in equilibrium. But in the JT expansion, during the process, the state is non-equilibrium. Only the initial and final state are in equilibrium. That's why I compare table form adiabatic expansion and JT expansion in a table form. The first point is that the system passes through equilibrium states in its passage. The system passes through equilibrium states in its passage from initial to final state. But in JT expansion, the system passes through non-equilibrium state from initial equilibrium state to final equilibrium state. Only the initial and final state are in equilibrium in JT expansion, and during the passage the system is in non-equilibrium. But in reversible adiabatic expansion, the during this process or every step is in equilibrium from initial to final state. Next point is that at any instant the system can be described by thermodynamic coordinates, because since the system is in equilibrium, therefore at any instant the system can be described by thermodynamic coordinates. But in the JT expansion, the only initial and final states can be described by thermodynamic coordinates. Next, the adiabatic expansion, the process is reversible. Here is reversible adiabatic expansion. But in JT expansion, the process is irreversible, because mechanical irreversibilities like viscosity, friction, etc. are involved in this JT expansion process. Therefore, the JT expansion is the process is irreversible process. Next point is that the temperature of the gas decreases. The temperature of the gas decreases in adiabatic expansion. But in JT expansion, I have seen in the porous plug experiment, the temperature of the gas after expansion either increase or decrease. If the initial temperature is sufficiently low, then the particular temperature or a certain temperature of a gas, then after expansion the gas becomes cooled. Otherwise the gas becomes hotter. If the initial temperature is not sufficiently low than a certain temperature of a particular gas, then the temperature of the gas after expansion becomes greater or increase. Therefore, in JT expansion, the temperature of the gas either increase or decrease depending upon the initial temperature. Either increase or decrease depending upon the initial temperature. The next point is that entropy remains constant in adiabatic expansion. Entropy remains constant in adiabatic expansion. But in the JT expansion, entropy increases because the irreversible process are called into play in JT expansion. Here is irreversible process. Here is irreversible process are involved. Here is irreversible process are involved. Therefore, entropy increases in JT expansion.